In today's section, we're going to talk about section 3.2, Polynomial Functions. And really we're going to focus on, sorry as I throw Geogebra across the screen, graphing polynomial functions, right? So our focus is going to be on graphing. And so moving forward through the next couple sections or chapters, our focus really is going to be on graphs of functions. And remember, graphs are the sets of all solutions to an equation, or when we think about functions, it's the all ordered pairs that map the input x into our output y, right? Or x and f of x. And so I'm going to revisit our definition of a polynomial. A polynomial function of degree n is of the form f of x equals a sub n x to the n plus a n minus 1 x n minus 1 all the way down to a1x plus a, let me see if I can close this GeoGebra for now, plus a 0. No, it does not want to go away, so that's a 0. And we had some special names for some of these terms. So we had a sub n x to the n was our leading term. And then an specifically, that constant in front of our leading term, we called our leading coefficient. And then a sub 0 we called our constant term. And remember, we call this degree n because that power, the largest power on x is n. And so polynomials have at least two features. Polynomials have two features. The first is that they're continuous. And remember, when we were talking about piecewise functions, we might have something that goes here, and then it jumps and does something else, and then it continues somewhere else, right? And so this graph is not continuous because there's a jump. But polynomials will always be continuous. In addition to always be continuous, they'll be smooth. So an example of a curve that isn't smooth would be our square root of the absolute value of x. So square root absolute value of x. And let me go ahead and square root absolute value of x. Because what we notice here at 0, our graph on the side, we end up with this corner. So if I draw my coordinates, the square root of the absolute value of x has this point. So this is not smooth. So polynomial functions, therefore, so polygraphs, not to be confused with a polygraph. So polynomial graphs will have no jumps and no corners. And this is important because what we're going to end up doing is we're going to identify some key characteristics of polynomial functions, namely, so key characteristics. That's end behavior. And then we're going to do, related to that, called the leading term test. We're going to find the zeros, and then we're going to find the sign. And with that information, we're going to be able to sketch our polynomial graphs. And so first, let's start with a subset of polynomial functions called the power functions. Let me get rid of this graph over here. And let's start with graphing x squared. This is our quadratic. We talked about our quadratic in our last section. And then if we look at, say, x to the 4th, x to the 6th, x to the 8th. And let me zoom in so we can see a little bit more what's happening. How about x to the 10th? And then just for good measure, we'll do x. Oh, that's x to the 10x. That's not what I want. X to the 10th. X to the 10th. X to the 1. X to the 100th. So as we increase with n even, so I'm going to first talk about the case when n is even. So n even. We have our starting point. So I'm going to mark 1, -1, 1, and I'll put in my point. So here we have x to the 1st. Nope, that's not how we write x to the 1st. We write it as x to the 1st. And then we go ahead and bring up another x squared, like this. And I said x to the 1st, and that's not even, n has to be even, so that's not a 1, and that's a linear. So let me get my eraser. That one was x squared, and then we had x to the 4th, and then we had x to the 6th, and so on and so on. And if I would go ahead and carry out this x squared, right, it'd be something not quite as exaggerated, but it would look something like that. Let me go ahead and bring my graph back. We can see as our exponent increases from 2 to 4 to 6 to 8 to 10 to 100, this value between 0 and 1, make a different color, this part decreases. It gets smaller in value as n increases. But over here, our value gets larger as n increases. And we have the same trend on this side, where this part decreases and this part increases. And so if I were going to generally write that, whenever we have some power functions, if n is a positive, even integer, our graph is going to do one of a number of things. It's going to go from 1 to -1, up to 1, because 1 to any power will be 1, and -1 to any power is going to be, -1 to any even power will be 1. So our function, generally speaking, is going to fall within this range. It's going to be either smaller here or bigger here. Right, so any n even is going to fall within this range. It doesn't matter what our exponent is. If it's, say, 24, it's going to be somewhere in here and up like that. Right, so n, a positive even integer, is going to fall into that area. And we saw that over here on our graph in Geogebra. So let me see if I can easily delete them all. It doesn't look like I can. So let me go ahead and delete these and start to think about our library function for x cubed. So power functions. And now we're going to look at odd integer degrees. So we'll start with x cubed. Right, and so now our library function looks like that. If I go ahead and start with my coordinate plane, 1 cubed is 1, but now negative 1 cubed is negative 1, and 0 cubed is 0. And so our starting shape could look better than that. Switch back to my pen. Something like that. Not perfect, but it works. And then let's compare what happens when we have, say, x to the 5, x to the 7, x to the 9, x to the 101, x to the 1001, and it's struggling to display that because it didn't keep my exponent. Let's do 161. Right, and so now we have a slightly different pattern. Notice after we get to 1, they still diverge. And maybe zooming out will show that the best. And so we have x to the 3, and this part between 0 and 1, it's still going to be true that it increases or decreases, and this part increases. And so again, the whole point here is to show you that when we graph our power function of odd degree integers, so power function with odd degree exponent, which is maybe redundant, it's going to fall into this category here, and this category, or this section down here, this section here, and this section up here. And so our cubes are going to look something, or our even degrees, or our odd degrees are going to look something like that. And you're like, so what's the point of all of this? The point of this is as follows. No matter what our function degree is, if it's even, it's going to have a particular end behavior. So end behavior. If n is even, it's going to be pointing up like this. It's going to do something in the middle. It might go below the axis. It might not. But it'll do that towards the ends. And if n is odd, we're going to have it going up here and down here. Might do some number of things in the middle. And this one even could go something like this. But every polynomial, so let me add a little polynomial end behavior. For n even is going to look something like this whenever a is positive, and n odd whenever a is positive is going to look like this. So what happens if if a is negative? So end behavior. If a was positive, we had either this or this with something in the middle, with something in the middle. But when a is negative, so say negative x squared or negative x cubed, we have a reflection about our x-axis. And so now we'll have something going down on both sides, or on this one, they're going to swap spots, down, up, and then something in between. So end behavior for even and odd. Whenever it's x squared, we always have two tails pointing in the same direction, and when it's odd, we have two tails pointing in the opposite. So let's look at a couple examples. Identify the end behavior of 2x cubed. 2x cubed. That was a really bad 3. 2x cubed minus 2x squared plus 1. So whenever we end looking at end behavior, we only need to look at this leading term. Leading term. So we have 2, and 2 is positive, so a is greater than 0. And x cubed, 3 is odd. And so that means our graph, its end behavior, we don't know anything about the middle yet, but we'll have an increasing there and a decreasing there with something in the middle. So let's just go ahead and check that with our graphing calculator. So 2x cubed minus 2x squared plus 1. So zoom out, and it does indeed look like we're going down. And can I just, nope, if I zoom out, it is making my x-axis smaller, but y is staying about the same. But even if we zoom in, we can see up to the right, it's going up, and down to the left, it's going down. Let's look at another example. We have x plus 2 cubed times 2x plus 1. And so if we would FOIL this out, and we won't do it in detail, we would have an x times an x times an x, so we have an x cubed, and some more stuff, times 2x plus 1. Which means in our final, we're going to have 2x to the 4th. That means a is positive, n is even, And so if we were to graph it, we're going to have something like that. We have, and we'll go ahead and type that into our graphing calculator, x plus 2 cubed times 2x plus 1. Enter. And we'll zoom out. And it's hard to see. It looks like it does something weird there in the middle, but towards the top, it does in fact increase in both ways. What actually looks like it happens is our graph comes down, touches the axis at what? Negative a half or negative 2, and then it drops down and comes back up. So it has a weird little kink, but it goes like this. And we don't know how to graph this manually yet. All we're looking at now is what's called our leading term test. And so let me give you the formal statement. Leading term test. A polynomial function f of x equals a sub n x to the n plus a n minus 1 x to n minus 1 a1 x plus a 0 if n even and a greater than 0, a less than 0, so positive and negative. So a polynomial function f of x, generally a sub n x to the n plus a to the n minus 1 plus all the way down to a1x plus a0. If n is even and a is positive, has n behavior like this. And if a is negative, it has n behavior like that. We don't know what happens in the middle. Something happens. We know it'll be smooth and continuous, but that's our n behavior. And if n is odd, a positive means our n behavior looks like this, and a negative means our n behavior looks like this, with something in between. We don't know what yet, but something is happening in between. So we're building up to being able to sketch a graph of a polynomial function. And the first thing we need to know is the general shape. So whenever n is even, we have what's called a parabola. And let me give you that name. So n even. This is called a parabola. And when n is odd, we have this cubic curve. So this is n odd. And so this is our general shape. General shape. And we know, given the sign of a, we know its n behavior, where it's either going to go up both left and right for a positive and n even, or both of them are going to go down for a negative and n even, or we're going to have them kind of going one down and one up if n is odd, and then where they are depends on if it's positive or negative coefficient. So we know its general shape, a parabola or a cubic curve. We know its n behavior. And now we need one more thing. Zeros of polynomial functions. Now the following are equivalent. That means they mean the same thing. Sum C is a 0. C is a solution or root. C is an x-intercept. And this x-intercept is going to end up being one of our most important. And x minus c is a factor. And so seeing that both x minus c is a factor, which in turn means that c is a 0, is important because then if we have a polynomial, and we can write it in terms of x minus c's, and we might have c1, c2, c3, different c values, we know that that's an x-intercept. And so let me revisit this example. We had f of x equals x plus 2 cubed, 2x plus 1. So that meant that x, if we want to know where f of x equals 0, we know that x plus 2 cubed equals 0, or 2x plus 1 equals 0. Well, here we have x equals negative 2, and here we have x equals negative a half. And so from our previous list, x minus c being a factor gives us the x is 0, but these are our x-intercepts. And so that means that this polynomial function, when I graph it, negative half, negative 1, negative 1 1/2, negative 2, is going to have a point at each of these. We don't know exactly what's happening, but if I go ahead and zoom way in on this, notice there's that point at negative 2, 0, and there's this point at negative a half, 0. And I also want to point something else out. I pick a different color. We had this 3. Notice that this curve around negative 2 kind of looks like our cube function. But we also know our end behavior, because remember we said that x cubed times 2x means that we had a 2x to the 4th, which means we have something up like that and something up like that. And so you can already see how we're starting to get close to our graph. And so we need to do just a couple more things to fully get us there. And so I'm going to keep using this example because it's a wonderful one. F of x equals x plus 2 cubed times 2x plus 1. So the exponent on a factor gives us the multiplicity of the root. So x plus 2 implying c equals 2 has multiplicity, and that's not just plus 2, because I said x minus c is a factor, so x minus negative 2, so c equals negative 2 has multiplicity 3, and x equals negative 1/2 has multiplicity 1. You're like, well, why do I care? Well, so x equals negative 2, multiplicity 3, x equals negative 1/2, multiplicity 1. Our rule is multiplicity. If multiplicity is odd, the graph crosses the axis. If the multiplicity is even, it touches but doesn't cross the axis. And so we're going to look at some more examples here where we're going to get to see all of this in practice. But because our multiplicity on x plus 2 or at negative 2 is 3, notice on the graph it crosses the axis. And our multiplicity at negative 1/2 is odd. It's 1, so it crosses the axis. Let me go back to my previous example. So here we had f of x. Let me get my eraser because I don't like how that looks actually. Did I go? Oh, I didn't go back quite far enough. Oh, I accidentally switched program. Well, now I'll just erase that. Get that back up here. F of x equals, in my previous example, 2x cubed minus 2x squared plus 1. And so we need to see if we can factor this. And can we? So, it doesn't look like we can factor this one because we have a cubed. And even if we would try to, say, take out just one of our values, we're not going to get to something that factors evenly. So we won't use that as an example. But thankfully, I've given us 4 more that we can. So, graphing a polynomial. Let me give you our steps. Graphing a polynomial function. So 1, identify end behavior. 2, find the zeros and their multiplicity. 3, find the y-intercept. Notice when we find the zeros, we already get our x-intercept, so now we find our y-intercept. 4, we can check symmetry. Check for symmetry. 5, determine sign of f of x in the intervals between the zeros. And then 6, draw the graph. And you're like, well, that's an awful lot of steps, Dr. Dubs. Well, let me go ahead and I'm going to go through each of these steps on our next example. Suppose we have f of x equals negative x minus 1, x plus 3, x minus 4. And so, first we need to identify end behavior. So we have a negative x times x times x. So we have negative x cubed. And so let me go ahead and I'm going to get rid of Geogebra for just a second, if I can. It doesn't seem to want to go away. Throw it over there. Nope. Alright, well, it's here to stay, apparently, because I can't get rid of it. Oh, there we go. Negative x cubed. So we have negative x cubed, which means that we have something that looks like this. and this. That's our end behavior. Our zeros are x equals 1, -3, and 4, which means at -3, 1, 2, 3, we have this. At 1, 2, 3, 4, and 1, 2, 4. So we have something that looks like that. Multiplicity 1, for each of those, they cross the axis. Symmetry, we could check symmetry, but I would say generally speaking, it doesn't help me all that much. But you would do that by comparing f of x and f of negative x. And I would say generally you can go ahead and skip that if you'd like. And then we need to determine the sign of our function. So let's see, we have this -3. Let's check x equals -4. And then between -3 and 1, so we'll check x equals 0. And then between 1 and 4, we'll check x equals 2. So x equals 4, or -4 rather. F of -4 equals -4 minus 1, -4 plus 3, -4 minus 4. So we have -4 minus 1 is -5, -4 plus 3 is -1, and -4 minus 4 is -8. We have negative, positive. 8 times 5 is 40. And so here at this point, we go up pretty far to plus 40. And then between -4 and 1, let's check x equals 0. And let me go ahead and erase this. X equals 0. I'll pick a different color just to keep it organized. X equals 0. F of 0 equals -0 minus 1, 0 plus 3, 0 minus 4. Negative, -1, 3, -4. We have -1, so we have +1 times 3 times -4 is -12. And notice this is our step for finding the intercept, -12. So at 0, we're all the way down here at -12. And it's smooth and continuous, so it has to go something like that. And then we need to see what happens between 0 and 4. So we'll check at x equals 2. X equals 2. F of 2 equals -2 minus 1, 2 plus 3, 2 minus 4. We have -2 minus 1 is 1, 2 plus 3 is 5, 2 minus 4 is -2. We're at a positive 10, and so once we get to here, we're up at positive 10. And then we have to check one more point on the right side of 4. So we'll go ahead and check 5, f at 5. F of 5, 5, 5, 5. -5 minus 1 is 4, 5 plus 3 is 8, 5 minus 4 is 1. So we have -8 times 4 is 32. So we come through that point and down. And that is our graph. And you're like, okay, well, let's check it because we have our graphing calculator. So there's no reason we can't check it. Our input is negative, parenthesis, x minus 1, x plus 3, x minus 4, enter. And zoom out, and let me change the color because that's a not great color. Settings, color, settings, color. Red sounds good to me. Close our settings. And actually, let me go ahead and make this full screen. If I can. Technology is great when it wants to cooperate. But when it doesn't, it's not so great. Nope, I'm going to have to graph it again. What a bummer. Let me type it again. Negative x minus 1, x plus 3, x plus 3, x minus 4. And now I can zoom out. Notice that we hit our point 0, negative 12. Zero, negative 12. And we have our 3 zeros at negative 3, 1, and 4. And so we have those points. We have our end behavior where it goes up to the left and down to the right. And our signs were negative, positive, and negative. So let me go back to Bamboo. Wants me to do a survey, and I'll pass. And that is exactly what that looks like. So we had, let me pick a different color, where we had this general shape here. And if I go back to my graph, that's exactly what it looks like. So this might feel a little nebulous right now because there are a lot of things we're doing right. We have to identify end behavior, our zeros, our y-intercept. But let's go through another example. For our second example, we have the following function. F of x equals negative x squared times x plus 1 times x minus 2. And so first we identify our end behavior with the leading term test. So end behavior. So we have negative x squared times x means we'll have a negative x to the 4th. Well, that already gives us then that our graph will, with end behavior, something like this. Then we look at our zeros, and we have a 0 at x equals 0, at x equals negative 1, and x equals 2, which means at negative 1, 0, and 2, we have zeros. The negative 1 has multiplicity 1, 0 has multiplicity 2, and the last has multiplicity 1. That means we have a cross, a touch, and a cross. Then we check our y-intercept. Well, we already know that there's a 0 at x equals 0, which means, just to double check, our y-intercept is f of 0. which is negative 0 squared, times 1 times negative 2. Well, 0 times anything is 0. So that is indeed our y-intercept. And then we need to determine our sign in some intervals. And so I would say a good way to do this is to make a little table. So we have a 0 at negative 1, we have a 0 at 0, and a 0 at 2. And so pick a point in each of these intervals. We'll try negative 2, we'll try negative 1/2, we'll try 1, and 3. So we need to look back at our, let me pick a different color, our original function, negative x squared, x plus 1, x minus 2. Well, we'll have a negative 2x squared is a positive, negative 2 plus 1 is a negative, and negative 2 minus 2 is a negative. So we have negative, 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 which means overall this part is negative, which means to the left of this we're negative, and we have to cross. At negative 1/2, we're going to have negative, a positive, and a negative, which means we're positive. And then at 0, we're at 0. At 1, we're negative, positive, negative. So we're back positive. So we're just touching and go back up. And then at 3, we have negative times a positive, times a positive, times a positive. So we come up, come back to the axis, and go down. And we have something that looks like that. So here we used our end behavior. Let me pick a different color to go over all of that. So this is 1. And then we have 2, 3 was our intercept, 4 is our signs, and I'm not going to write any more up there. And then we have that picture. So let me go ahead and go to our graph. And here we have negative x squared, x plus 1, x minus 2. And I would say this matches pretty closely what we thought we had. Because we cross here at negative 1, we touch at 0, and we cross at 2. So let's go ahead and look at one more example. So here we have, and let me pick a different color, f of x equals x minus 2 squared, x minus 2 squared, x plus 3 squared. So if we multiply this out, first we need end behavior. We have an x squared and an x squared. So we have positive x to the 4th. So something like that. We need our zeros. We have one x equals negative 3 and x equals 2. Multiplicity 2, which means that it's going to touch at negative 3, 1, 2, 3, and touch at 2, 1, 2. We need to find our sign in our intervals. Actually, I skipped a step. 3 is our y-intercept, so f of 0 is negative 2 squared times 3 squared. So 2 squared is 4, 3 squared is 9, so that's 36, and so way up here at 36. Now we can find our signs. And so we know that we have our interval breaks at negative 3 and 2. One we already found at 0 was 36, so let's find it at 3 and negative 4. So here we have negative squared, negative squared is positive. And at 3, we have positive squared is positive. And so it's positive. It's going to come down and touch the axis. We'll pretend, let me erase that and try again. It's going to come all the way up to 36, and come back down and touch the axis, and come up this way. And so let's go ahead and graph that on our graphing calculator and see how that compares. No negative out front. X minus 2 squared. X plus 3 squared. Enter. And that looks pretty spot on. Go back to Bamboo. Let me see if I can get this up here. I have to zoom out a little bit more because it's so steep, but that's pretty good. And so really it'll become more comfortable to graph polynomials as you do more. The important things to remember, and let me bring this over to this side if I can. There are a couple important things to remember. So let me pick a different color. Things to remember when graphing polynomials. You need the end behavior from the leading term. We need zeros and their multiplicities. We need our intercept. If x equals 0 isn't already a 0. We need to find the signs in the intervals. Then we can sketch the graph. And then I'm going to add a new one, check with Geogebra or a graphing calculator, whatever you have access to. And that is how we graph polynomial functions.